Good day, my name is David Russell. I'm an inventor machinist, and today I'd like to share with you an invention that has taken me over 46 years to figure out. I call it a mechanical piston apparatus. I'll get up and just turn my camera around a little bit, just give you some idea of the size of it and what it looks like. And I'll slowly turn the camera so it doesn't jiggle too much. Basically it's a couple of gears with a couple of bearings mounted on it. And it's compressing the beam, which is on top of the scissor beam. That when that beam gets compressed, it stretches out on this end right here against a straight wall, which is connected to a rack and gear. Pinion assembly is stepped up to 3-to-1 ratio, and at the bottom, hanging on this sprocket here, you can see I got a 20-pound weight suspended. And what I'm going to do is I'm going to turn this digital scale on here and apply a force to this rack on top of the two gears. That's going to turn those bearings and start compressing that beam. And that beam is its force is going to be transmitted forward to lift this 20-pound weight that's already suspended. And we're going to measure the force it takes to lift it. Now this here will be at a 1-to-1 ratio when the whole machine is all put together and assembled. But this here is not the whole machine completely assembled, put together, but I don't need the rest of the machine right now for the final test of the demonstration of forces. You can see the other end of the scissor beam is securely clamped in place. It will not move. And only this end here is the part that will be moving forward once this beam is compressed. Now you see underneath there's a set of springs that hold this beam up. And what's going to happen is, you can see on the wall behind, I know I can zoom in there or not, but let's check it out, see if I can. There's a cam assembly drawn up that I sent to the AutoCAD place in the States there. They're trying to do up a 3D demonstration of this project, and they needed this drawn here to add to it. That beam there will fit on the end of this shaft here, on the end of this shaft, on this gear. And what it does, these bearing blocks here are spring loaded, and I'll zoom back out again and I'll show you what happens when this gear is rolling forward. Those cams will hit those spring loaded bearing blocks and force those bearings here, excuse me, these bearings here, it'll compress them in by pushing these two bearings here on top. And what happens is, once these are compressed in, the springs will lift this assembly out, and the other tube bearing, the other beam on the other side now takes over the load. So this will be the weakest point of the machine, so I'll leave this at that. Now what I'm going to do is two force tests, one with the springs loaded and one without the springs not loaded. So the first test is with the springs loaded. I'd say it's going to take roughly close to 14 pounds of force to lift that 20-pound weight. Let's turn the scale on and do a demonstration. All you have to do is see this little pointer move here. Maybe I can move my camera over here so you can see it a little better. I don't know. How does that look? Alright, anyway, keep your eye on this pointer. This pointer that's on the sprocket, a couple magnets, and I'll get the digital scale and hopefully focus right. You can see the readout, it's about there, I'd say. So it's going to take around, like say, 14 pounds. 12, 13, 14, yeah, a little over 14 pounds. Do it again. 14 pounds. Okay. I'll do it again. Excuse me. There we go. Okay. Now, turn that on. The next test, I'm going to, like I say, I'm going to disconnect those two springs in the back and the bottom there. And then we'll do another force test. And in this force test, we will not be stretching those springs on it, so it'll take a lot less energy to lift this weight. And it doesn't take much to disconnect those springs. I'll run over right now. And this way I disconnect them. I just bring down there. That's that one. And so now we have the springs disconnected. Welcome back over to the digital scale again. Same 20-pound weight that's suspended here. And do another reading. See how much force it takes to lift that same weight. So I'll turn the scale back on. And this time it should take roughly 4 pounds of force to lift the same weight. So we'll try to get my scale so you can see it. And it does. It takes 4 pounds of force to lift it. So that shows the law of physics, how it works in this mechanical device. I think it's going to be a very useful mechanical device for mankind worldwide, because it's going to produce clean, free, pollution-free electricity. That's my goal, what I'm going to do with it. So, right now, I'll shut it down to decide what to say next. Alright, take a break. Thanks. Okay, now that we have the force demonstration done, the first question most people are going to ask is, how is this unit a 1-to-1 ratio? The unit itself here is just a half a section of the complete machine, which the other section I'll demonstrate after this. It's when the two are joined together that makes it into a 1-to-1 ratio. But as for the demonstration tests, I tested it as it is, as if it was a 1-to-1 ratio. Even though this mechanism itself is not 1-to-1 ratio, because the end of the beam is clamped on the other end, and it's not moving. And the forward distance that's being compressed here from the input force, it doesn't move at a distance of 1-to-1. But the input force on the rack above and the chain lifting, the weight, is 1-to-1 ratio. So to demonstrate that, I got past videos and pictures of that section of the machine. I'm going to try to pick one out. The one I pick it out is going to be a little shaky because I'm holding the camera with my hand, but it gives a good description of how that section works. And when you see what that section looks like, it'll give you some idea that when this section here is joined to the end of it, basically a better understanding of how the machine works. So that's what I'm going to do. I'll go onto my computer now, dig that one up, and see if I can get a video put together here. I think the world needs this knowledge and information, especially at this time amongst this global pandemic that we're living in. The world is in a bad state right now, and some good news like this hopefully will cheer some people up in the world and give them a brighter future to look forward to in the not too distant future, when we can get a handle on this disease that's going around, and wipe it out, and at the same time bring forth a clean, pollution-free energy source by manufacturing and building machines like this mechanical piston apparatus. That there's to be, and hopefully in the not too distant future. So in the meantime, enjoy the rest of the video that I'm going to try to put together here. Thanks. Okay, I'll try not to shake the camera too much. Here's the picture of the wall post track assembly. As you can see, it is quite a large machine sitting in my living room, but it happened to turn out to be this size due to the fact of past inventions I tried to build. I just used the same parts over and over again. So there's an end view here, little ball weights here, 6 gears, bearings mounted on each side of it. Now the main thing I want to show you about this is that as this rolls along the track, the bearings that are sticking outside of the gears. Alright, let's go back to the start over there. You see at the very end, if that bearing there hits the top of that, that's 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11, and 12. Then it's back to 1 again, over at the end. So these gears have 6 bearings mounted on each side of it, which is 60 degrees apart. And then on the other side of the gear, there's 6 more bearings mounted. They're also 60 degrees apart, but they're offset 5 degrees from one side to the other. Okay, let me try to show what I mean here. Right, this one, and then it's 5 degrees down, next one, then 5 degrees down, the next one, 5 degrees down, 5 degrees down, 5 degrees down, so on, right across the line to the end. And as you can see, it starts at 1 there and ends at 12 here. And what happens is, as these roll along, each bearing goes from 1 to 12, then back to 1 again. Throughout the whole duration of the trip of this gear rolling down the track, it moves these wall posts on a separate track, like so. Now, if it's getting near the end there, you have to have the output force the same as 1 to 12. So we'll start over here at number 1. We'll try to look at it. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and that's 12. Then it's back to 1 again over here. And it just starts over and over. So you have to have the output in to match the input in. That's about the hardest part of the machine to design is the lengths of these pieces like that are in, because this here, these motions here, it's like a snake-like action. If it was just a straight line, you can see how it's curved. And that matches the timing of these at the start. So that's an important part of this machine. Now I got to tear all this apart. I'm going to strip all these gears. I'm going to strip all these bearings off it. And then I'm going to assemble what's laying on the floor over here. And you see, there's a couple of beams for the mechanical piston engine assembly. And some of the parts. So I'm going to use the same base that's underneath this thing holding this up. And we'll put together the mechanical piston engine assembly. Just a small portion of it to demonstrate the final force test. That's all I'm going to be demonstrating. And it's not the whole machine completely finished, because as you can imagine, if I join that on the end of this, which it will be, right here, the mechanical piston assembly up there on the wall here is going to be attached to the end of these here, right here. You know, on the end of each one of these. So This section here is just called a wall beam assembly. At the end of that, there's a rack and gear, which is 3-to-1 ratio, stepped up. So when this unit here moves backwards a distance of 2 feet, those sprockets will roll a distance of 6 feet in a linear distance. So it brings the machine back to a 3-to-1 ratio, same as this. Excuse me. When this machine rolls forward a distance of 6 feet, this axle here that I'm pushing with my hand, this wall track unit here will only move forward a distance of 2 feet. So that makes it a 3-to-1 ratio. So that's why we have to step it up with that 3-to-1 ratio there on the input end to bring it back up to a 1-to-1 ratio. Now, that's basically straightforward about how this part of the machine works. And as I tear it apart, like I say, I'll describe how you go about setting it all up. You can see the angles here, the curvature it makes, all these bearing blocks offset 5 degrees from one side to the other. These little weights down here just pulls the wall tracks back. These units here. Oh yeah, another thing I want to show you and point out is that when this bearing here is down on the vertical section of the wall post, right here like that, you can pull on the wall track and push on it backwards, and that bearing a ton of force, and will not put no pressure on the axle here to go back that way. I can demonstrate that, and I pull on it. And you see it doesn't move. I can pull on my weight and it won't move. But yet I can easily move forward. Excuse me. Okay, I'm going to shut my camera off now and set it back up in the tripod and start dismembering this section of the machine. And just do the opposite when you go to assemble it again, and it should all work out exactly the same as it is right now. Okay, later.